Swayam Prabha. Digital India. Educated India.
Welcome back to the lecture series in bioelectrochemistry. So we are into the 9th lecture or the 4th lecture of the second week. So we are into lecture 9, which is basically week 2 / lecture 4 of week 2. Okay, W2L4. Okay. So today we will resume on standard potentials, where we have discussed previous 2 classes. Standard potentials. Okay. So in the last class, if I go back, if you remember what we talked about was, so we talked about the hydrogen electrode, standard hydrogen electrode, and I told you that this is the first kind of electrode. While the next section, while we will move on to, after the post-Nernst equation, we will move on to potentiometry and electrode, you will realize. So this is the first kind of electrode what we have dealt, which is standard hydrogen electrode consisting of a platinum metal, where it is being continuously infused with hydrogen gas, whose activity is of course 1, as we mentioned, if you remember it. This is hydrogen gas, and this is kept in a HCl solution, hydrogen chloride solution, where H plus ions activity is 1, and there is a equilibration which happens across this electrode, on this electrode. What is happening is that there is an equilibration like this, where this is the platinum surface shown in green, and this is the aqueous medium where H plus ions are present. One second, let me, okay. And the equilibria which is being developed out here is something like, as I had shown you in the reaction, H2, and you can again rewrite it. There are different books which will put it something like this: standard hydrogen electrode reaction, standard hydrogen electrode half reaction will be basically H plus, okay, in aqueous with an activity of 1 plus electron. It's a reversible reaction. What you are getting, half H2 hydrogen gas, which is gaseous phase with activity of 1, which is essentially the same reaction. And what is important here to know, the stream of hydrogen which is bubbled through the electrode saturates the solution. So what you are seeing here is, this is out here, essentially what is happening is that this hydrogen which is being bubbled through this, okay, this hydrogen bubbling which is coming, this is essentially the stream of hydrogen bubbled through the electrode saturates the solution with aqueous hydrogen, okay. So in other words, you are having out here aqueous hydrogen, this is getting saturating with aqueous hydrogen, and the activity of the gas hydrogen is unity if the pressure of hydrogen is 1 bar, and the reaction that comes to the equilibrium at the surface of platinum electrode is being shown here. So this is essentially is the standard hydrogen electrode reaction, the half reaction, and what is being done to it is, so arbitrarily assign a potential of 0. That's what we have discussed, okay. This is not totally arbitrarily defined. Number which is as 0, okay. So arbitrarily defined potential 0 to standard hydrogen electrode at, so 25 degrees centigrade. So keep this in mind. So the voltage measured by the meter in figure 13 points figure out here, in this particular figure where we saw the hydrogen electrode going through out here. So the voltage what you are observing is very interesting when you attach this half cell to the another half cell. So essentially now what is happening, try to understand the reaction what is happening. Silver is there, which is a surface which is getting reduced. So from the solution Ag plus goes and deposits here and looks for an electron. Now in this situation what is happening, the electron from here are flowing. So silver, and what you are observing out in the meter is a positive. So now you remember the axiom what I was trying to tell you, positive 0.799 volt. Why this is important? So if you remember that I told you something earlier, okay. So I'll go back to that. One of the previous classes I told you about the potentiometer, where the potentiometer will stand. So if you recollect, this indicates the positive voltage out here indicates when electron flows into the negative terminal. So you are observing a positive voltage out here, it means electrons are moving on to the negative terminal. So electron flow is like this. So from the standard hydrogen electrode, the electrons are flowing in this direction and they are eventually reaching here where Ag. So what was the reaction we started with? Our reaction was this one, where silver ions from the aqueous medium, so silver ions are traveling from the aqueous medium on the surface of the Ag metal, and out here this silver is obtaining an electron and becoming Ag. This is a reduction reaction which is happening, and your potentiometer is showing a volt of positive 0.799 volt, and this is very important value because this is the value which is essentially the standard reduction potential. Okay, so for the reaction Ag plus electron making Ag solid, and so the standard reduction potential is, which is positive 0.799 volt. Okay, and the positive tells us that the electron flows from left to right through the meter. So the electron is flowing from left, this is your left and this is your right, and electron flow is happening like this. That is what gives you a positive value out here. Now this part is exceptionally important for you to understand, and in future this will come very handy, and that's why I am taking so much time on all these things. So we have arbitrarily assigned a potential of 0 to the standard hydrogen electrode at 25 degrees centigrade, and the voltage measured by the meter is being shown as plus 0.799. Okay. Now this is another thing what I wanted to highlight, because this will come handy, because from standard hydrogen electrode we have moved to different other kind of reference electrode, as we will talk more about the reference electrode. So it is something like this. Say for example, I say the water freezes at, say water freezes at 0 degree centigrade. Okay. Now if water freezes at 0 degree centigrade, then we say that hexane boils at say 69. So let me take two examples. Hexane boils at say 69, and benzene boils at 80. Okay. So the difference between the two, what we essentially did when we have cadmium and silver electrode. So the difference between the two will be 11 degrees centigrade, right? Now say for example, if this is we are talking about water freezing happening at that point, okay? Now suppose I change the reference from 0 to say 200 degrees centigrade. I change the reference, arbitrarily I change the reference. Then what will happen? These two values will be shifting to say 269 and 280. Still the difference will remain 11 degrees centigrade. So in other words, what I wanted to highlight through this analogy is you can always develop other kind of simple references as long as you calibrate your reference electrode with a standard hydrogen electrode. And as we will move through, you'll realize there are AgCl, silver chloride electrodes, which are used as reference electrode, because you have to realize one thing: you cannot carry a standard hydrogen, like you cannot carry a hydrogen cylinder all the time to have the standard being set. Practically it is not, I won't say not feasible, but practically it is something like a very cumbersome thing. So, but why we are studying it? Because this is where all the tables, all the charts, all the basics are there. But then from there we shifted. It's something like, say for example, I say 0 degree. So I set the, say freezing at say 200 degree or something, it doesn't matter. So I can change the reference with respect to one standard reference, and as long as those reference and the deviations from the reference are the same, I do not have to worry. So as we will move forward, you will realize that there are different kind of electrodes where people have used different references, but those references were calibrated or are calibrated with standard hydrogen electrode. But the first one where all these assumptions came was started with arbitrarily defined standard hydrogen electrode as at 25 degrees centigrade as 0. So it has a potential of 0 with respect to it. So for this reaction, the reduction potential, in other words, if I had to understand physically, what does that mean? Physically, that means what is the power with which it can pull an electron towards it? What is its reduction power? Its reduction power is expressed in volt in terms of potential. What is your potential? Could you clear this exam? Could you get this to you? Could you pull this bucket? Could you pull the electron? What is your power? Your power lies in plus 0.799 volt. And that is your power. Now anything higher than that will have more power. In other words, anything, say for example, I say 0.7, okay, I say 0.8. So 0.8 means I have more power to pull the electron. I will be pulling electron faster than you. And anything lesser than that, if I say a negative value, so imagine. So that will give us a different kind of situation. It means that has lesser power than one we have defined in terms of pulling the electron. So again, you can define it two ways, as I am repeatedly telling you. Try to demarcate. You can tell it that what is the power to give away the electron, which is you are getting oxidized. So in that case, it will be defined as, instead of standard reduction potential, it will be called as standard oxidation potential. But generally, we do not define it like that. The general thumb rule which most of the books will follow, and I am going to follow, is a standard reduction potential. In other words, what is the potential with which it can pull an electron towards it instead of giving away electron. So we are not dealing with this, but theoretically, yes, you can always talk like that, okay. Standard reduction potential. So if you know the power, that this is the power with which you can pull an electron, then you can calculate the work done. How you can do? If you know the amount of charge, you remember EQ, work done, voltage multiplied by the charge. So that way you can say, on this electrode, this much work is being done by the electron, okay. So you are realizing how we will correlate all these things with those very first class, if you remember very earlier classes in the first week, I told you about all the different formulae. If I just have to go back, if you remember where we have talked about all this work done and all those basic parameters we talk about. Here it is, work done, you remember? So now if you know the E, which is your in volts, okay. So say for example, I say 0.799 volt, and if you know the charge on the electron, then you can, and how many electrons are moving, then you can calculate what will be the work done. So see, all these basic formulae are coming back into the place. Now if you know the work done, then from the work done, what you can do, you can calculate the power. So work done per second, work done per second. So that will give you the power of the cell. So that brings us to those very words you heard. This battery has this much power, or this cell has that much power. Where all these things are getting derived? These are getting derived from these very simple equations, and that's why I'm taking so much time on the basics. If you understand these basics, then everything will make sense to you. Similarly, from there you can calculate the delta G, which is N out here, okay, which is in the moles, Faraday's constant, and E you know. So if you know this, then you can calculate the free energy. So with one small value, you can really open up the whole gamut of things, what all you can do. So you need couple of parameters. So essentially the two parameters where everything works is either you have the voltage or you have the current. If you know either one of these two, you can really play around very neatly with the system, okay. So that's why I wanted to go back, and let me come back where I am. So this was a very early, and I want you people to revise through those basic things, that from these values we can do the work done, what is the work is being done, and how much work is being carried out in the whole process, okay. So from here we will move on to, I will now show you a practical table. I'll put a table in front of you that will give you an idea. So for example, this is just a small part of the table. You will find most of these tables, or maybe I will add one into fluorine, which is F2, gaseous state, plus 2 electron, making it 2F minus, okay. I'm just putting all the different O3, which is ozone, gaseous state, plus 2H plus 2 electron, making it O2 gas plus H2. Similarly, MnO4 plus 8 proton plus 5 electron. These are the different compounds. I'm just giving an kind of example of Mn2 plus 4 H2O, okay. Similarly, Ag, we have already talked about it, Ag plus electron, Ag solid, copper 2 plus 2 electron, making it Cu solid. Similarly, 2H, now this is the reaction what we have already talked about, H2 gas, okay. Now cadmium 2 plus 2 electron, making it cadmium solid, okay. Similarly, potassium plus electron, making it potassium solid, okay. Similarly, lithium plus electron, making it lithium solid. Now you remember one of the values, right? This value all of you remember. Now what I am giving you is E0 values on this column, E0 in volt, E0 standard reduction potential, and these agents. So if I had to really split it up, I didn't put all of them in line, but I'm just okay. On this side what you are having are the oxidizing agents. So you remember oxidizing agents are the ones which get reduced in the process, and reducing agent which gets oxidized in the process. Okay. So, if you remember this value, this is 0. This is what we have assigned it. Now, you remember for silver it was positive 0.799 volt. Now, copper, which is plus 0.339. Okay. Similarly, for fluorine, it is 2.890, and these are all experimentally determined values. Similarly, for oxygen, once again, this was for fluorine, and oxygen is out here, which is 2.075. For manganese, it is MnO4, it is 1.507. Now, if you go below hydrogen, this is where you are falling. Cadmium minus 402, 0.402, potassium minus 2.936, minus 3.040. Now, I told you something. I wanted to show you that picture what I drew earlier out here. This is that reference. You remember? I told you that there is a reference. With reference to it, we have certain things which are on the negative side, which are on the positive sides. Now, coming back, here is your situation. What does this physically means? Physically, if you look at this picture, say fluorine has a value of 2.890 as compared to silver, which is 0.799. So, let us write down the value 2.890 volt, and you have silver 0.799 volt. Now, in this situation, say for example, I make a cell of silver and fluorine, just imagine for the imagination's sake, and I ask you the question, who is going to pull the electron faster? Because someone has to pull the electron faster. So, in this case, that 2.890 volt of the fluorine will tell you, you can immediately look at, oh, this has much more positive value. It means it has more power to pull the electron. So, if these two are starting and there is an electron sitting out here, say for example, this is the electron somewhere out here, this is the electron, and these two, my two hands, say for example, I place it like this somewhere, okay, something like this, okay, I place it, and these are the two, one is fluorine and the other one is silver. Who is going to pull the electron faster? This fluorine. So, this is going to capture the electron faster. So, it means if I make a cell with fluorine and silver, the electron will flow away from fluorine, sorry, from silver to fluorine, because fluorine has a much more power to pull the electron towards it. In other words, work done for the electron to move will be much more higher in case of fluorine as compared to, much more spontaneous as compared to silver. Now, think of a situation. We had this cell when we talked about a cadmium and a silver electrode. Now, cadmium and silver, when we made that cell, what we showed, now if we go back, so we showed that in that case the electron, so cadmium is getting oxidized and the electron is moving from left to right to the silver electrode to reduce the silver electrode. Then we had this standard hydrogen electrode. Out here we showed the electron from standard hydrogen electrode moves and reduces the silver. Now, how we could figure that out? Because our voltage was showing on the negative terminal electrode is reaching. Now I give you a situation where again we have the same situation. On this side we have the standard hydrogen electrode SHE, and on this side, this is the half cell, we have the cadmium electrode. Okay. Now we wanted to measure the cadmium. The standard hydrogen electrode is attached to the negative terminal of the potentiometer pot, and this is the positive side. Okay. So now what will happen? Now in this situation, by the convention, the left hand side is a platinum electrode attached to the negative reference terminal of the potentiometer, and the right hand electrode is attached to the positive terminal. Okay. Now in this situation, in order to measure the standard potential of the half reaction of cadmium 2 plus 2 electron making cadmium, or in this situation it is basically cadmium CD2 plus 2 electron, where it is giving away these 2 electrons. Okay. So this is a situation. Now what we are observing in this situation is, so you have on one side the cell is like this, standard hydrogen electrode SHE, CD2 plus in aqueous with activity is equal to 1 and CD solid. And what we are observing is, it is showing you out here, if you follow the chart, it is showing you negative voltage, and the negative voltage is minus 0.402 volt, which is, that means in this situation this electrode, standard hydrogen electrode, has more power to pull the electron as compared to cadmium, because the electron flow is now happening in the reverse direction like this. And if you remember the axiom I told you, when the electron is reaching the negative terminal of the potentiometer, you will see a positive shift. If the electron is reaching the negative terminal, sorry, the positive terminal of the potentiometer, if the electron is traveling, follow the diagram, if the electron is traveling to the positive terminal of the potentiometer, then you will observe a negative voltage, and that's precisely is why you see. So in other words, what is the physical meaning of it is that if there is a competition between standard hydrogen electrode versus cadmium electrode, then standard hydrogen electrode has more power to snatch the electron towards it as compared to the cadmium electrode. And that's why you see the electron will be drifting in a reverse direction from right to left, unlike left to right, what used to happen in cadmium on the left, silver on the right, left to right electron drifting. Standard hydrogen electrode on the left, silver electrode on the right, electron is drifting. Now cadmium electrode on the right, on the left you have the standard hydrogen electrode, electron is drifting from right to left, and your meter is showing a negative voltage, which is 0.402. So I believe with this background of understanding standard potential, standard reduction potential, you will be able to draw your own story. So the negative sign means that the electron flows from cadmium to platinum, a direction opposite to that of the other cells. So with this background, I want you to kind of revise through, because I took 3 classes purposefully on standard potentials, because this is one concept which will come very handy as we will move through. So what we will do, we are into the second week though. And we have talked about only one kind of electrode, which is standard hydrogen electrode. In the next class after this, we will talk about the Nernst equation followed by the series of electrodes what we will be dealing with. Okay? So, I again advise you, please concentrate on the basics. It is all about the basics, and I am only churning out the most important aspects what you needed to know as a biologist to do bioelectrochemistry. Please get your basics right, please. So that's why I'm going very slowly. I'm not really worried about the bulk what you know. What is important, you know the basics very well. From one set of values, you should be able to back calculate what is happening, how much work is done, how these things are happening. So please, 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 it's my kind request, please concentrate on the basics. I'm going slow for you people so that you understand the basics once and for all. Okay, so I'll close in here. In the next class, we'll talk about the Nernst equation and we'll follow up from there. Thank you.